I want to thank everybody for having us here on behalf of myself and my colleagues at US Bridge. We want to talk a little bit about the advantages and versatility of steel bridges. This presentation is primarily about truss bridges, which is what I've been dealing with for the past 30 years at US Bridge. Steel bridges, they're used for many purposes and lengths, and for this discussion we're primarily going to talk about steel truss and beam bridges on rural highway systems. One may ask, what is a truss bridge? The three main types of rural truss highway bridges are, of course, on the left is the deck truss, where the structure is underneath the roadway. In the middle is the through truss. It's an old standard where the vehicles pass through the middle of the structure with overhead portals to stabilize the truss. And of course, on the right is the simple pony truss that we see in a lot of the rural areas anymore. Truss bridges are composed of straight members connected to form a stable configuration. Individual truss members are primarily either in tension or compression. So for start out, the bridge floor, it provides the traveling surface that carries the wheel loads. The floor transmits these wheel loads to the stringers. The stringers, of course, span between the transverse floor beams. The transverse floor beams apply the loads to the truss joints. The truss joints pick up the loads and convert them to the truss members in either forces of either tension or compression. Of course, the truss bridge is one of the oldest bridge types still being used today, and these were used they were analyzed in the 19th and 20th centuries by engineers using hand calculations. Anymore with the computer systems and everything, it's much more easier and faster. They can be designed to meet all current AASHTO specifications, ASTM Material Standards, and the AWS Welding Code. Of course, original trusses we used to see were the wooden covered bridges. That was simply because the wood was more abundant, and the local people constructed them on site. They added a roof and siding just to protect the wood structure from the elements. After wrought iron and steel became available, metal trusses were more common from about the 1870s through the 1930s. Before the 1870s, it was a kind of a mix between wood and steel. Wood and wrought iron, really. Of course, these early trusses, they were really labor intensive. Steel was expensive. Labor was cheap. And they required a lot of complicated false work just to build them on site. Modern trusses, they're typically fabricated into modular units, and they're bolted together at the job site. These modular prefabricated bridges, they started out as portable structures years ago, and over the years they've developed into the fully permanent. Of course, these prefabricated trusses anymore can be built without using the temporary false work. They're more stable. They can be lifted with the cranes. The trusses be set, the internal components be reached out and set. Crane capacities and sizes are much more available than they used to be, so it eliminates the need for the false work. And also they're more rigidly constructed, and you've got a lot more options on lifting them. Sometimes it saves to build the entire structure, bring a large crane in, set the unit on the abutments in one piece. Now, the reasons we want you to build some truss bridges. This is a little bridge down in Virginia near Washington, D.C., leading to a housing development. Of course, they call the bridge, it's the Crooked Bridge Road. They built this multiple span beam bridge, and the flood debris moved the piers. They used the bridge until last summer, and finally the DOT came by and put a stop on the use of it. So with the clear span truss, this is not the same location. The Crooked Bridge has not been replaced yet, but When it is replaced, it'll be a clear span. All the waterway obstructions will be removed, and they won't have any more problems. Underslung floor beams, like it shows in this picture, you can use that configuration to minimize the finished roadway to low steel. In this case, with the floor beams underneath, the floodwaters can actually go above the floor beams and flow through here. I've always had a lot of debates with engineers over this method. You know, of course, a lot of them say the low steel for the floor beam is the lowest point you want to use, but you can still get about 2 to 3 feet of more water. Debris will hit on the ends of the floor beam. A lot of times it'll wash and continue on around it. Not all the time you can raise the roadway on the approaches to use a different configuration. And of course, these underslung floor beams are the most common that we've seen historically in the older bridges, excuse me, and the newer ones. The raised floor beams that we're doing, the design is considered equitable, structural design is considered equitable, but the truss structure is dropped down about 12 inches. The floor beams are raised between the trusses. The stringers are formed and bolted between the floor beams, but it gives you a lot cleaner look under the structure. It's a preference. Some engineers, like I say, prefer the underslung, some the raised. Of course, with the truss, another thing, the substructures can be built totally out of the waterway and eliminating a lot of your environmental concerns. I was talking to a bridge engineer of North Carolina a few years ago, and he had some environmentally sensitive areas that for some kind of an endangered fish or whatever, mussel or whatever, he had to put $1 million in a fund to prove that he would not cause any danger to these. He said by building trusses, he can move back on the land. He doesn't have to put all this money in a fund to hold, and he was quite happy with it. Truss bridges also have a high strength to weight ratio, and you can use existing abutments. In this case, this was a very rural bridge down in West Virginia. The state highway forces removed the old pin-connected through truss. It was a case where the school buses could not cross the old bridge. They would park one bus at one end of the bridge, walk the kids across, load them on a bus on the other end, and take them on. At night, they reversed it. So with reusing the existing abutments and a new truss, they got by a quick solution, and it's a single lane road, but the buses use it, and it's been a proper fix for several years. Of course, these trusses can be configured to do different options. You can combine the vehicular roadway and the pedestrian sidewalks. The sidewalks can be either on the inside of the truss or the outside. With the trusses, the main structural components are above the roadway. So it's an ideal location for railroad overpasses. Getting your spans up above. You can work your floor beams into the grade. This bridge was on a skew and a grade. Floor beam hanging below here. It's raised up, and then on the other end, so it's sort of a skewed and cambered combination there. One of the reasons this problem, bridges used to be built with a 20-foot clearance back in the 30s, and recently the clearances have raised to 23 feet, because they're going with more the double-decker cargo, train cargo carriers. So with the truss, you can take a lot of these existing roads and match the existing grade with, without doing a lot of extra work. You can drop the floor beams below, raise them over the middle to get your 23 feet of clearance, and drop them back down again on the other side. The truss actually stays at one point. You pick the point that you're the most clearance. You set the truss at that elevation, and then you work out the connections for the trusses or the floor beams to fit the profile. This condition here, they had to increase the height maybe a foot or so at the end, but they only tapered it out within 50 feet of each end of the bridge. So it saved the county a lot of money on approach roadway work. Sag vertical curves, they can also work out with the truss. In this case, coming down this hill, if it used a plate girder or a large rolled beam to do this 120-foot span, to pick up the elevation difference from the bearings to the back wall, this would have been a lot more fill over on the right-hand side. Again, environmentally, it saved any work encroaching out on the lake. Of course, with steel truss fabrication anymore, everything is inside plants under controlled conditions for drilling and welding and all the layout. You can build the entire truss. You can, and do all the weld testing, inspections can be performed. The trusses can be, in most cases, can actually be put together and tested for fit up. Some states require that before it's ever shipped to the job site. Actually, before you want to put any finish on it. And speaking of finish, you can also do the 3-coat paint systems right in the shop, then ship it to the site and do the final touch-up after the bridge is erected. One thing that's come up here in the past 15 years is hot dip galvanizing of truss sections. These sections can be fabricated in the shop in modular pieces that will fit in an available tank. This section is being dipped in a 60-foot long tank. It's about 7 feet deep, 5 feet wide. So only half of the truss can be fit down in the tank. In this case, they're pulling it out. They're cleaning off and allowing it to drain. It's turned over, ran through the flux line again, and acid washed on the other side. Then they're double dipping it. Once the coatings for galvanizing and painting have been installed, it's usually delivered to the job site. And this is kind of an extreme case. This shows a 120-foot truss span loaded over the headache racks, and it was delivered 40 miles from the plant to a site. So it was a pretty rare occasion that large of a truss unit would be shipped out. Typically, they're shipped out into smaller legal loads that are stacked and just with normal trucks, stacked and delivered to normal trucks. One of the things we've also run into recently is rehabilitating the old historic steel trusses. Common practice for many years was just simply to bypass the old trusses and just leave them standing in the same location, and they're just allowed to deteriorate. I've seen many trusses that were bypassed like this, and you go by it 20 years later, and it's like, why? What's why can't we save that? It may be a significantly historical structure, and there's been a lot of work in the past few years for that. This is an example. It's 108 feet by 13 foot roadway, and the bridge was hot dip galvanized. Started out as a simple span wood deck, very rural road. To the left of the picture, there's just out of the picture, there's an old water-powered grinding mill, for a grain grinding mill, and the county engineer wanted to do something to save the bridge because the state conservation department was working on rehabbing the mill. So we took the bridge down, completely rehabilitated it. It was actually an old interurban sort of train. It carried interurban train cars, and so it was pretty heavy duty. So there was not a lot of work had to be done to upgrade the bridge, other than take it apart, clean up the normal corrosion in the joints, and a couple of pieces were replaced. But everything was put back together after it was hot dip galvanized. A325 bolts, new bearings, new gusset plates. There was some of the new bottom cord replaced here. Of course, these gusset plates were replaced. The rivets that were secure were left in. The vertical had a lot of rust, so they were cut off about 6 feet above the bottom cord, and new sections were spliced in. Everything bolted back together. The unit was taken back to the site, laid on the ground, bolted, assembled in one piece. The pieces were stacked. Lifting sleeves were built around them to protect it from the cables from cutting the finish. And all this was done right near the site. The truss was simply lifted with a crane, swung into place, and set on the abutments. Because the abutments were widened and reworked a little bit. This is concrete with form liners. It was so it made it look like stone abutments. The caps were, of course, they were used as form liners also. The existing abutments were below here. The trusses were set up, guide off to hold them in place. The intermediate floor beams were installed. The top portal bracing was put in, and the bridge was partially completed in one day. And of course, it had a final design was a concrete deck. It had shear studs that were attached prior to galvanizing. The completed bridge actually had a twin steel tube design, crash-tested railing, concrete deck. It was limited in height and width, but it carries the design for HS20 loading, like I say, with crash-tested railing and everything. So another bridge was worked on was metallized. A metallized finish is a galvanized coating that is thermally sprayed on the steel pieces. I prefer first the hot dip galvanized. Second my preference would be the metallized finish. The hot dip galvanized finish is much more durable, easier to work with in the field. the metallized finish is a little tougher than paint, but it still has the edges will flake off easy, and it's a little tougher to repair in the field. This bridge was disassembled using scaffolding setting in the creek. The creek bed was solid rock. The unit was taken apart, set off to the side with cranes, disassembled into smaller pieces, transported back to the shop, rehabbed, metallized, brought back to the site, reassembled. Each unit was set in the creek is the frame that was used to pick up the spreader frame to pick up the units. The abutments, of course, they were reworked and poured with the same kind of form liners on the other bridge. There were new, get closer here. There were new floor beams, new gussets, some new verticals. There was actually a lot of these plate bottom cords replaced, although these are the existing. You can see some of the little nicks and scratches in them were from the years it was in service. But it had new stringers, new floor. Again, the unit was just set out on the temporary scaffolding. The lifting frame was taken to the other side, hooked to the other half of the truss, and then that unit was set in place. All the connections were made, and of course then later the floor was added, and the railing and the approach pavement was placed. So this bridge was built in 1887, I believe. It was rehabbed in 2005. Another bridge with a shop painted finish. Little rural road, had 3 or 4 houses. The people absolutely loved the bridge. They decorate it in the wintertime with Christmas lights. And so when the county engineer was talking about replacing it, they stirred up a little fuss, and he actually got federal enhancement money to restore and work this this bridge. If he had waited on normal funding, I think he told me that normal funding was down the road about 5 years. He checked into it, found there was this historic enhancement money available, and he did the project in the same year he applied for the money. Of course, the old bridge, it had some things that had to be replaced. So there was to take it down, there was a temporary piling drove to stabilize the trusses while everything being removed. There were temporary lifting beams added to the top, temporary bracing, and the U-bars holding the floor beams, they all had to be replaced. So the day that it was removed, they were just simply cut out, allowed to drop. They had a cable on them, they just pulled them out of the water. The reason the bridge was removed is the abutments were in such bad shape that the specifications called for the bridge to be removed from the abutments, set on the approaches, rehabbed, painted, and on the approaches. New abutments were supposed to be built, and then the trusses were put back in place, but as one unit, of course. But it was easier and cheaper to take the bridge and clear apart into all the components and take it back to the shop, rehab it, paint it with the 3 coats, bring it back to the site, lay it on the ground, reassemble it, put the same lifting units back on it, reassemble it on these new abutments. These new abutments over here. In the same manner we took it down. The bridge, the way it was originally manufactured on falsework, was such that if we simply lifted it without any stiffening, we would have lost it. Some of the sections would have fallen apart. So we had to add a few temporary bracing, just to keep the bridge together. And again, like we had the lifting beams was the same as when we took it down. And the floor beams, they were stiffened by adding plates, or bolt-on plates, top and bottom flange, and new U-bolt hangers. There were 4 vertical bars for the floor beam hangers on each end. The rest of the bridge was original. It did have a posting when the bridge was finished. I forget what the posting was. Here's one of the new units, that was new bars, the vertical bar that's here. All these U-bolts were replaced. Of course, the new stringers. The temporary bracing we used on top came out later as we put the original portals back in. And then the floor, it had a wood strip floor put down, and the rail was it wasn't crash tested, but it was based on a crash tested design. Bridge was opened that same year. We took the bridge down in April, opened it to traffic in August. So it was a pretty timely project. I'll talk a little bit. This is a bridge that is a new bridge built to look historical. It's starting to run out of time here, so we'll have to breeze through some of these. Another bridge built to replicate a historical bridge that had to be removed. It was upgraded to HS20. Of course, with new piers and abutments, with the form liners. Guide rails, everybody talks about crash-tested rail systems on bridges. That's not the way you do it, though. Most of the trusses can incorporate standard crash-tested systems that are already out there. This is a tri-beam rail. Here's the New York DOT's. They have 2 tubes. Of course, there's a full parapet, full concrete parapet. This is Ohio's twin steel tube. It's kind of in the background here. Twin steel tube. This is on the approach as a curve. The twin steel tube attached to the concrete deck. Texas has been doing a truss-mounted crash testing for a rail system. They have a rail that mounts to, there's a bracket on the batter post and each of the verticals. That tube is a Schedule 80 steel pipe, about 10 inches long, 10-inch diameter, mounted to this is the vertical off the batter post, and this is a 6x6, I believe it's a 3/8 thick tube. This is, of course, continuous across the bridge. On the ends, on the approaches, it's not finished here yet in this picture, but there's some kind of a concrete parapet that was added. And of course, it had an open grid floor. There's a website I can give you where all this stuff, information's at about this crash testing railing. Of course, simple stand steel beams, fabricated really similar to the trusses in the shop under controlled conditions. Steel beam bridges are simple, basic beams, diaphragms, a floor system. railings. We're going through these. A lot of them are designed for self-installation without any specialized equipment, and the length's based on the availability of the beams. Any finish. Use existing abutments. Faux trusses can be added, or as we've done in a few places. Mostly they're rural situations. This was in Texas. They added the concrete finish to an arched steel beam. The finishes are galvanized, weathering, and there's been a lot of simple span steel beams used for railroads, just from rolled beams. About finishes up my time, and I want to thank you all for, and I'll be around the rest of the day if you have any questions.